The session this morning will be chaired by Miriam.
Okay, so I'm very happy to announce the first speaker, which is Eric Cavalcanti, and he will tell us about semantics for counterfactual in quantum causal models. Please go ahead.
Thank you. It's a pleasure to talk to you today. It's a real shame I couldn't be there in person, both because it would have been great to share in the discussions, which I'm sure have been very interesting, and because I haven't been to Berkeley since 1999, when I was an exchange undergraduate student there. Sorry if I may be a bit slow, it's 2:30 a.m. here in Australia, but I think hopefully I'll be okay. So today we're talking about this joint work with my student Adra Kudari-Suresh and my postdoc Marcus Frems on the semantics for counterfactuals in quantum causal models. And this work was partly funded by an ASC Future Fellowship and a large grant from the Foundational Questions Institute. Okay, can you all see the screen? Yeah. So let me start with a story. When I was a small kid, we used to live in a high-rise apartment in Rio de Janeiro, Brazil, much higher than in this picture. I often looked out the window and I wondered, if I were to jump, would I fly? And at some point I was convinced that I could. It's bad influence from some TV shows. And one day when I was maybe 2 or 3 years old, I put a Superman cape, pushed a couch next to the window, and with the help of my sister, was 11 months older than me, I climbed up and I was ready to jump, I think. And my mom arrived just at the nick of time and, "What are you doing?" And my sister said, "He's gonna fly." And then it's commotion, and my father arrived and said, "Oh, why don't you practice first from the table?" And so after several unsuccessful practice jumps and maybe some bruises, I decided that I needed more practice. So I remember that night having a vivid dream, and I was looking out the window on the same spot. My mom didn't come, so I jumped, and then I crashed. And it became a recurrent dream. I remember having that for many years. And that's probably why I remember that story vividly, even though I was so small. And I gave up the idea of flying, of course. And they say that one of the purposes of dreams is to simulate the effects of our actions, the counterfactual effects of our actions. And I think there's some truth to that. In my case, at least, there was certainly an evolutionary advantage, I could say. So let me ask you, had I jumped, would I have flied? And I hope all of you will agree that the answer to the question is no. So counterfactual questions can be meaningful, and they appear routinely in everyday discourse, and we make intuitive judgments about them. Questions like, what if I had jumped? What if Oswald had not killed Kennedy? Given that the patient died, what if they had not been given the treatment? Some of these questions may determine life and death, and may determine praise and blame, or medical mistreatment trial. Or even more importantly, what if we stopped emitting greenhouse gases? But the semantics of counterfactual questions has a controversial history. One of the most cited early accounts, though not the first, was due to David Lewis. He proposed to evaluate counterfactuals via a similarity analysis of possible worlds. And that's following also Robert Stonecker. And he said, a counterfactual, if it were the A, then it would be that C is non-vacuously true, if and only if some accessible world where both A and C are true is more similar to our actual world overall than it is any world where A is true, but C is false. Now, he also said, counterfactuals are infected with vagueness. We ordinarily resolve the vagueness of counterfactuals in such a way that counterfactual dependence is asymmetric. And then he proposed a system of priorities to resolve this vagueness in terms of possible worlds. I'm not going to do anything like a full review here. What about causation? David Hume is often quoted as identifying causation with mere regularity, or as doing away with causation altogether. But as pointed out by Lewis, he defined causation in 2 ways, as a regularity and also as counterfactual dependence. He said, we may define a cause to be an object followed by another, and where all the objects similar to the first are followed by objects similar to the second. Or, in other words, where if the first object had not been, the second never had existed. And so Lewis said, I take Hume's second definition as my definition, not of causation itself, but of causal dependence among actual events, and propose a counterfactual analysis of causation. And it assumes determinism, it must be noted, as also does his theory of counterfactuals. Now, cutting a long story short, to get closer to the topic of this workshop, counterfactuals feature at the top of Julia Pell's ladder of causation. Pell's work identifies a hierarchy of progressively sophisticated models that answer progressively sophisticated questions. At the bottom of the ladder is the level of association related to observations and statistical relations. It answers questions such as, how would seeing X change my belief in Y? And the second rung is the level of intervention, which consider questions such as, if I take aspirin, will my headache be cured? And the final rung is the level of counterfactuals, which is associated with the activities of imagining, retrospection, understanding. And they consider questions like, was it the aspirin that stopped my headache? And Pell has argued that levels 2 and 3 are particularly important for human intelligence and understanding, and they are crucial aspects of our modeling the world and the effects of our actions. And he also argues that current artificial intelligence, however impressive, is to a level 1 of the hierarchy of the statistical association, and thus the little robot there. Maybe arguable, but that's down. Considering now the coming age of quantum computation, one of the motivations for this work is to extend Pell's analysis to the framework of quantum causal models, which may have potential utility for quantum AI, but more importantly, I think it is, an interesting fundamental and philosophical question. So level 1 association is which encodes statistical data. There is a probability distribution over various variables. And probability distribution can always be encoded as some Bayesian network, which is a directed acyclic graph representing statistical independence relations. And a distribution is said to be Markov relative to a graph G if it is possible to factorize the distribution in such a way that each variable is conditioned only on its parents in the graph. But in general, there will be many Bayesian networks which are compatible with the same probability distribution. So here's some examples of factorizations according to some graph. And that at this level, the graphs don't carry causal meaning. They're just a convenient representation of the independence relations. At the level 2 of the hierarchy, we have the causal Bayesian network. So here the arrows between the nodes encode causal relationships. So a causal network is an oracle for interventions. It encodes the potential effects of interventions that an agent may do in the system. So a due intervention where you set the value of, say, variable A to a given value, the lowercase a, is calculated by this truncated factorization formula, which can be conceptualized as this mini surgery in the graph, which cuts the errors going into that node, which is being intervened upon, and setting the value of the variable at the node to some specific value. So here's the graph for G, and here's a graph that you get if you intervene on G to set A to be equals to A. In the level 3, we have structural causal models, or probabilistic structural causal models if the probabilities are included. So this consists of a DAG with a set of endogenous variables, here the V's, a set of exogenous variables, U, which can be thought of as local noise variables, which are determined only by factors outside of the model, and a set of functions that determine each one of the variables as a function of its parents in the graph and its corresponding exogenous variable. And a probabilistic structural causal model also has a probability distribution over the exogenous variables. And it's easy to see that a probabilistic structural causal model induces a causal Bayesian network over the endogenous variables by marginalizing over the exogenous variables. Now, in temporal metaphor, Pell's 3-step algorithm for counterfactuals now evaluates a counterfactual as in terms of a structural causal model. So a counterfactual is a question of the type, given evidence E, what is the probability that Y would have been little y had X being little x? And so Pell proposes 3-step algorithm to calculate that, which is composed of abduction, action, and prediction. In the abduction step, we update the probability distribution for the exogenous variables by the evidence to obtain the probability of U given E. In the action step, we replace the equations for the variables in X, and there could be a set of variables, by a particular value. That's doing a do intervention. And in the prediction, we compute the probability for Y using this modified model. And in a temporal metaphor, the step 1 explains the past, the exogenous variables, in light of the current evidence. Step 2 minimally bends the course of history to comply with the hypotheses, with the antecedent of the counterfactual. And step 3 predicts the future based on our new understanding of the past and our newly established condition. So note now 2 similarities with Lewis's analysis. Here, counterfactuals are evaluated assuming determinism. And so counterfactuals have well-defined truth values. And a minimal deviation from actuality is implemented to satisfy the antecedent. Now, one important distinction from Lewis is that while for Lewis, causation is explained in terms of counterfactuals, for Pearl, counterfactuals are explained in terms of causation. And here I take the same perspective, the same point, the same approach, explaining counterfactuals in terms of a quantum causal model. Now, so far so good, but now, as we all know, quantum theory throws a spanner in the works by a number of noble theorems that show that classical causal models cannot explain certain quantum correlations while satisfying a number of a priori reasonable assumptions. The most well-known of these is Bell's theorem, which can be stated as showing that classical causal models, in particular the representation of causal structures of DAG and the causal Markov condition, together with relativistic causal structure for a particular scenario, here being, say, Alice and Bob in the space-like separated lab, X and Y being choices of settings, and A, B, the observed outcomes, and lambda, full specification of the common causes. And if we also assume that the interventions, the choices are exogenous, they have no relevant causes, we obtain the Bell inequalities, and thereby contradiction with quantum correlations, the contradiction with observed data, regardless of quantum mechanics. Okay, so that's one issue. And another, which may not be well known for those who are not working in quantum physics, in particular in quantum foundations, there's also a more recent no-go theorem by Chris Wood and Rob Speckens, who showed that if you don't even need to assume the particular causal structure that I showed in the previous graph that comes from relativity. If you assume, if you want your causal model to satisfy the assumption of no fine-tuning or faithfulness, that is that conditional independences must arise as a consequence of the graph and not due to special choices of parameters. So for example, if we have no signaling, we should expect a causal model which does not have causal paths between the setting on one side and the outcome on the other side. So assuming no fine-tuning, there is no possible graph which can explain the quantum correlations. And as I suppose many of you know, that assumption is important in causal models to allow in general for causal discovery. And then in 2008, I proved a stronger result based on that, without 2 extra assumptions from Wood and Speckens, and also allowed to generalize to quantum contextuality, but that's not important for the present purposes. And more recently with my student, Jay Pearl, not to be confused with Julia Pearl, Jason Pearl, we proved another result in full generality. So one alternative, of course, is to accept the violation of relativistic causality of faithfulness, and to accept that causal structure cannot be discovered in general. But in recent years, a growing number of papers have been produced on the topic of generalizing the classical causal model formalism to accommodate quantum correlations in a way that's compatible with relativistic causality and that allows for causal discovery and faithfulness. So this has led to development of frameworks for quantum causal models, of which 2 here highlighted in red, some of the more complete, which can be probably called a framework for quantum causal models. And this work will be based on a combination of features of these 2 formalisms. And by the way, Sally Shrapnel and John Barrett are both talking about their work at this conference, I believe, but unfortunately only on the last day. And so it would have good to have their introduction to it, but since that wasn't possible, I'll give a brief review of quantum causal models. But if you want to learn more, stay tuned for their talks. Okay, so what is a quantum causal model? In a classical causal model, a node represents obviously a classical random variable. In a quantum causal model, the nodes are conceptually very distinct. They are a locus of potential interventions. So a node A here, it has associated with it a pair of Hilbert spaces, which represent the input system and the output system to that node on which an intervention can be made. And in this work, we assume, like in the framework of Barrett and others, that the dimensions of the Hilbert space are the same as in order to allow for the possibility of doing no intervention having in that node. And a quantum instrument is a set of completely positive maps that sum to a completely positive trace preserving map. So here I represent the choice of instrument by variable Z. So that's a set of CP maps, and the outcomes are labeled by lowercase a. And if you sum those CP maps, it sums to a CPTP map. I don't label the instrument with this M because in general, the same CPTP map may have a decomposition in terms of many different instruments. Now, the key technical tool of quantum causal models is the Choi-Jeremiakovsky isomorphism. We use a version of the CJ isomorphism, which is essentially the same as that of Costa and Shrapnel, because it's simpler to understand, I think. But we use the notation of Barrett, Lawrence, and Oreshkov because it leads to a simpler statement of the quantum version of the causal Markov condition. And similar formalisms have been developed under various terminology, multi-time formalism, quantum combs, process matrices, etc. They're all talking about similar things in the different contexts. So the Choi-Jeremiakovsky isomorphism associates to every CP map. So here this MA given Z, a positive semi-definite operator, which here is called tau A given Z, which lives on the tensor product of the input and output Hilbert spaces. And it can be thought of as the state up to normalization, the state you get if you prepare a maximally entangled state between these two Hilbert spaces, and then you apply the CP map to this subsystem. And if you sum these operators, then they sum to the Choi operator corresponding to a CPTP map. And one property is that if you trace the output system, because it's a trace preserving map, it gives you an identity on the input. All right, so now let's consider channels between nodes. They say you have a node A1 and node A2 and a channel E from the space of linear operators on the output Hilbert space of A1 to the space of linear operators on the input Hilbert space of A2. So this is a CPTP map, a channel, that takes states from A1 to states on A2. And when it is quantum channels between nodes that we are talking about, the CJ isomorphism gets an overall transpose relative to the definition for instruments. And this is a convention so that the probabilities in the Born rule or the generalization of the Born rule are given by a nice looking rule without a trace, traces going all over the place. So compare these. This is a general transpose relating one to the other. All right, so now our quantum process operator, sigma over the nodes, is a positive semi-definite operator that lives on the tensor product of all these Hilbert spaces, such that for all choices of instruments at the nodes, so these is CPTP maps, the trace of this object here is 1. And the probabilities for observing the particular outcome of these instruments, A1, A2, etc., given choice Z1, etc., is given by this generalized Born rule. It has much the same form as the standard Born rule if you think of this as a state and this as a measurement operator. And similar objects go by various other names. Like I said, quantum combs in the Cousal and Shrapnel formalisms called the process matrices. And here we use this shorthand notation. A trace over A means a trace over A in and A out. All right, so now a quantum causal model is specified by a directly cyclic graph G with quantum nodes, A1, etc. A quantum channel for each node that goes from the parents on the graph to that node, such that all these channels commute. And the process operator is given by a product of these channels. And this is the quantum causal Markov condition. Now note the analogy with the factorization formula for the classical causal Markov condition. That's my reason to prefer this notation. Now consider the Choi operator for a unitary channel from input from Hilbert space AB to Hilbert spaces C and D. Okay. Yeah, not necessarily associated to nodes, just in general. Now we say that A does not influence D if and only for any state rho B that's prepared. If we're preparing product states here, for any state rho B that's prepared, it's not possible to send signals from A to D by varying the state at A. And this can be given a more precise mathematical definition, but that won't be necessary for this talk. Now, recall that in the classical case, the counterfactuals are evaluated relative to a structural causal model, which is represented by a set of functions associated to the nodes and exogenous variables associated with each node. In a structural causal model, we have full information about the process, and all lack of information is about the values of the variables at the exogenous nodes. That's where the probabilities come in. So we define then the quantum version of the structural causal model analogously is a DAG G of a set of quantum nodes, a set of exogenous nodes. There's a final node F that's not shown in the figure. There will be errors potentially from all the other nodes to it, so that will be cumbersome. And an unitary, the Choi, Minkowski, isomorphic operator corresponding to an unitary from the outputs of A to the inputs of A and from lambda to F that satisfies the no influence conditions that you can see represented in this graph. Each node is only influenced by its parents, and each lambda only influences its local node. And a set of preparation instruments, which we can think of as an instrument which, with probability P of lambda, prepares a state rho lambda in the output of the exogenous node, and just ignores the input. So now, summing over the elements of these instruments, we have an instrument that prepares the state rho, which is this particular mixture, particular decomposition of the state rho. Now, how do we decide what is the preferred basis, what the preferred decomposition for these exogenous instruments? This is an assumption the assumption is that comes from the model. A similar issue arises in the structural model. How to decide what are the exogenous variables? It may come from various physical reasons. For example, it may be because of decoherence, or it may be because we know that there's some setting on a laboratory device that there's some set, but we don't know the outcome in a particular operation, or from some other reason, whatever the reason may be. But the idea is that there should be some fact of the matter. So these should be, for all practical purposes, classical variables. It should be stable facts, to use the terminology of DBI to Ravelli. So the motivation for introducing this type of instrument is so that, just like in the structural causal model, now all lack of information about the process is attributed to a lack of information about events, physical events at the exogenous nodes. And now these are the variables over which we perform the abduction step for the evaluation of a counterfactual. Now we say that a process operator is compatible with a DAG G, and there's a slightly different definition in Barrett et al. If and only if there exists a quantum structural model associated with G that recovers that process operator as a marginal. Okay. And it can be shown, and also that follows straightforwardly from this proof in Barrett et al. For this different definition, that sigma A is compatible with the graph G if and only if it is Markov for G. Now, their slightly different definition is in terms of a unitary process with inputs, which is almost the same, as our quantum structural model, with the crucial difference that in that definition, there are no instruments at the exogenous nodes. These states are thought of as being part of the process. And there are no events associated with those states. Whereas here we want to think of those as being physical events, that we can imagine that there's a fact of the matter, at least for all practical purposes, about which one of those events has happened. And it's something that we can make inferences about in principle. So here we're able to do abduction. Now the proof, yeah, as I said, follows straightforward. Now, given the information, if we knew about all of these outcomes for the events at the exogenous nodes, we can define a conditional process operator, and this is following Cost and Shrapnel, which is the process operator for the endogenous nodes that we get, conditioned on knowledge about the outcomes at the exogenous nodes. And note that this is only well defined in general because the exogenous nodes have no causes. So this probability in the denominator doesn't depend on the instruments that are performed on the endogenous nodes. And so this can be used to calculate the conditional probability for a particular set of outcomes for these instruments, given lambda, just by the generalized Born rule with this conditional process operator. And here I'm using this notation with a bold letter A and Z to represent this tensor product of the instruments at all the nodes. All right. How much time do I have? Sorry.
I think about 10 minutes left.
Okay. So now let's consider the evaluation of counterfactuals. Now in Pearl's formalism, as we're seeing, a counterfactual statement can always be assigned a true value if you give a full specification of the exogenous variables. So one can define a probability for the counterfactual to be true as the probability that the background variables lying in the range of values where the counterfactual is evaluated as true. In a quantum structural model, on the other hand, a counterfactual will in general not have a true value, even given a full specification of the background conditions. And of course, that's because quantum mechanics in general doesn't give true values to statements about potential outcomes. So that means that we cannot in general ask for the probability for a counterfactual to be true, but rather we can only ask for counterfactual probabilities. In some cases, they will be 1 or 0, but not in general. So the most general counterfactual query that we can answer unambiguously in this formalism is what we call the standard counterfactual query, which is the following. Given that the set of instruments Z has been implemented and outcomes A obtained, what is the probability that outcomes C would have obtained for a subset of nodes had instruments Z prime been implemented and outcomes B obtained at a subset of nodes B? And notice that to get an ambiguous answer, we need in general to specify the instruments in all nodes, both actual and counterfactual. If that's not specified in the query, we may decide to interpret that as putting an identity instrument, as putting a no intervention. But that must be a specification, even if it's no intervention. All right, so now, yeah, we could also include cases where we have partial information about the observed outcomes, but it should be obvious how to treat that case, so the notation would be clunky for this talk, so I didn't do that. Now, given a quantum structural model, this can be evaluated similarly to Pearl's method in a 3-step process of abduction, action, and prediction. So for the abduction step, we want to infer what the past must have been, the stable facts, given the information that we have at present. So we want to update our information about the outcomes of these instruments, given the observed outcomes at the various nodes. And because all of these are effectively jointly measured variables, we can perform Bayesian updating to calculate the conditional probability for the lambda given A, and given that the instrument sets have been performed. So just do Bayesian inversion. We calculate the probability for A given lambda using that conditional process operator that introduced. Probability of lambda doesn't depend on Z, that's just the prior probability. And the probability for A is just given by the generalized Born rule. And so you can define an updated process operator, which is just a weighted mixture of the conditional process operators with the updated distribution for the background variables. So this is analogous to Perl's modified model. Now, for the action step, we modify the instruments at the endogenous nodes as required by the antecedent of the counterfactual. Now, unlike in Perl's formalism, we do not need to modify the process itself. We don't need to break errors, because an error breaking intervention at a node can always be emulated with some appropriate discard and prepare instrument that discards what's coming in the input and prepares some state at the output. Which state it is depends on the question we're asking, how to interpret that. Now, finally, we calculate the prediction for the required conditional probability using now the updated process operator with the counterfactual instruments, the instruments corresponding to the counterfactual query. Okay, and so here again, note this notation is a shorthand for a tensor product of various instrument elements. So if a counterfactual can be interpreted as a standard query of this form, then you will always have an unambiguous answer as above, but sometimes it's not. And so next, and that's part of the ambiguity that the vagueness that Lewis referred to, we will discuss the task of interpreting a counterfactual query that's not already in standard form. So in Perl's formalism, all counterfactuals are evaluated via a due intervention. And here we are allowing room to have counterfactuals where the action step does not correspond to a due intervention. In fact, it could even be trivial. And why? Well, in a classical structural model, given complete information about the background variables, all endogenous variables are determined. So this means that the only way the antecedent could have been different while keeping the background fixed is if some intervention had occurred. So Perl said, to model an action due x equals x, one performs a mini surgery on the causal model. There is a minimal change necessary for establishing the antecedent while leaving the rest of the model intact. This mini surgery, not unlike Lewis's little miracle, makes precise the idea of using a minimal deviation from actuality to define counterfactuals. Now, in a quantum structural model, even giving complete knowledge of the exogenous variables and complete knowledge of the process, having a unitary process, does not in general determine all instrument outcomes. So the antecedent could have been different, even keeping all of the background variables fixed and keeping the rest of the model intact, if the instruments are the same, and the probability of having obtained the outcome corresponding to antecedent is non-zero for all values of the background variables, which are non-zero given the evidence. Okay, so now we call a passive counterfactual one that can be evaluated without requiring an intervention where these conditions are met. So, for example, consider a scenario where you have two endogenous nodes, B and C, and an exogenous node lambda, which is just this preparation instrument. It prepares with probably a half, a state 0, and probably a half, state 1. And say the instruments at B and C are just measurements on this plus or minus basis. And the unitary is just an identity from lambda to B, from B to C. Now, we ask, given that B equals plus, what's the probability that C equals plus had it been that B equals minus? But now the probability of getting the probability of lambda given B equals plus is larger than 0 for all lambda, and the probability of getting plus is larger than 0 for all lambda as well. So we can answer as a passive counterfactual, and then the answer is that the probability of getting C equals plus had C equals plus had B being equal minus is 0. Okay, since I don't have a lot of time, I'm going to have to go a little bit faster here. Now, we can consider a slightly modified model where the preparation is in a different base. It's preparing the same state if you ignore the outcome, but now it's in the plus and minus base. So now those conditions are not satisfied, and the only way to accommodate the antecedent now is via an intervention. So we use due intervention, which just prepares the state minus at the output and ignores the input. So that's the analog intervention. And so we can answer this counterfactual query, which in this case turns out to be 0. We could have chosen different values that it could be different. Now note that this is very important, that this dual intervention is not the same event in the sense of not being the same CP map as the original one. So there's definitely some vagueness and ambiguity there about whether there's the right thing to do. It's in a sense analogous to the dual intervention impulse model. Now, how do we decide whether a counterfactual should be interpreted as passive or as active? Why not just use the active version? And the reason is that the motivation, as we saw in Poe and in Lewis, is that we want to make a minimal modification in the actual state of the world to consider the closest possible world. And the closest possible world is one in which everything was the same, but it happened that the outcome is different. So we can propose a principle of similarity. If it is ambiguous whether a counterfactual query is intended as passive or active, and it can be interpreted passively, then it should be interpreted as a passive counterfactual query. So now consider this case of a Bell scenario. Now we have two nodes A and B and a common cause C, which just prepares with certainty maximally entangled state. So the channels factorize in that way. And Alice and Bob say it is mattering on the computational basis. Now, given that A equals 0, what's the probability that B would have been 1 had A been 1? So by the principle of similarity, we should interpret it as a passive counterfactual because it's possible to do so. So the answer to that would be that it's 1. So A and B would be perfectly correlated, which is what we find. So here, then, in fact, the counterfactual has a true value. B would have been 1 had A been 1. But note that there is no causal dependence. So unlike, say, in Lewis' counterfactual analysis of causation, here counterfactual dependence does not in general imply causation. Now, if we were to interpret that as an active counterfactual, we'd get a different result. We'd get that there is no dependence between A and B if we interpret that as being a true operation at A. But again, this is further from the meaning of the outcome had been A, because it would have been a different event. So, and that was a further from the actual world because it requires intervention. So there's a good reason to interpret that as a passive counterfactual. That just means we get to a different conclusion about the relationship between counterfactual dependence and causation, as Lewis did and as Poe did. Now, just to complicate things a little bit further, there's also a class of counterfactual queries which consider counterfactual instruments in the antecedent, so it should be classified as active, but the counterfactual instrument is not a dual intervention. So you may call this active-observational counterfactual. I don't love this terminology. It may change it somewhat. So here, for example, imagine that we have that the counterfactual were the Alice could have performed a different instrument, a measurement on a different basis. So we say, what's the probability that B would have been 1 had it been that A equals 1? That's 1. What's the probability that B would have been 1 had it been that A equals plus? That is that Alice had measured this different instrument, obtained a common plus. The probability would have been 1/2. So there's a counterfactual dependence, but that's conditioned on the outcome. If we didn't condition on the outcome, we just ask what's the probability that because it had this different instrument being used, then there wouldn't be a counterfactual dependence. So one of the things that we know there is that conditioning on outcomes can create a counterfactual dependence without causal dependence if the counterfactual instrument does not block the input to the node as it does in a dual intervention. Okay. Now, in summary, then we defined a quantum structural model in a semantics for counterfactuals in analogy with those, and we find that in quantum causal models, the relationship between counterfactual dependence causation, which existed in Lewis and Poe, is broken. Now, counterfactual dependence may occur without causation. And counterfactual dependence is associated with causal dependence only for active counterfactuals, for those which include something like a dual intervention. Now, some limitations of this model. First, it's not intended as a general theory of counterfactuals. It's not going to answer what would have happened if Oswald didn't kill Kennedy. It's obviously only aimed at questions about quantum experiment. It's very hard to answer other kinds of questions with that. And also, different interpretations of quantum mechanics would have given different answers. For example, in Bohr mechanics, it's a deterministic theory. So something more like Poe's analysis would be implied by that. The difficulty there is that we cannot know exactly what the causal structure is in chain. Now, another limitation is that quantum causal models do not resolve the measurement problem. So this is something that I argued in this paper 2016, and then more recently in this paper with Hal Wiseman, there's a talk that I gave in a recent workshop, which is based on this noble theorem from our group at Griffith on the Wegener's friend paradox. So if you're interested, just go and watch the talk or look at that. And so the upshot is that the classical and quantum causal models are, we can think of them as both effective theories. They are pragmatically useful at different levels of description. Classical causal models are useful in the classical limit, and quantum causal models are useful when, for all practical purposes, we can say we have a fixed Heisenberg constant with quantum systems on one side and classical systems on the other side, and we can unambiguously identify the outcomes of the interventions. So some further questions is there's a long debate about the idea that quantum mechanics violates counterfactual definiteness, which has been discussed in very vague terms. Again, it's an interpretation-dependent question, but within this interpretation of counterfactuals, it can be given a more precise statement of what it means to violate counterfactual definiteness. Also, which I didn't mention there, relationships with things like contextuality. And also, I looked at very simple cases with not very interesting answers in this talk, but could there be more interesting applications of that? For example, in cryptographic scenarios, would I have observed something different had I been an eavesdropper? And also more general, more interesting causal networks. Thank you.
Thanks very much. There are some questions in the room, so I think we'll start here.
Thanks. Can you go back to Pearl's ladder? I think it's 11. Oh, you went by it. Yeah, there.
Mm-hmm.
So this is something that just bothered me about Pearl.
Mm-hmm.
And I just want to get your, the way he has that set up, just literally on the page.
Yes.
You have some kinds of systems that can only do association. Okay, so they're just doing statistical analysis of observed facts, right? And that's kind of clean.
Mm.
And then you got the next step up, the doers, which are cavemen somehow, and then the imaginers, right? And
Right.
it's by these three levels. Now, it seems to me that just isn't right for the following reason. And it's connected with another piece of terminology. So they're subjunctive, pure subjunctive conditionals. If X were the case, B would be the case, which are uncommitted as to whether X is or is not the case.
Sure. Yes.
And then there are
contrary. I'm conflating counterfactuals with subjunctive.
Right. Then there are contrary to fact conditionals, counterfactuals, where implicitly you're asserting the antecedent wasn't the case. Yeah.
Sure.
But if you're a doer, right, if you're interested in practical decision making, what you want to do is evaluate pure subjunctive conditionals about what would or might happen were I to do action X or were I to refrain from action X. Yeah. And compare those things and then make some choice. But that means you're already answering questions about pure subjunctives. Now, if you think you've got the pure subjunctive, if I were to jump out the window, I would fall. And you don't jump out the window, you're committed to believing if I had jumped out the window, I would have fallen, right? So the pure subjunctive commits you, if you give it a truth value, it already commits you to the counterfactual in the case where the antecedent doesn't actually obtain. So this whole picture of there being these three steps arranged in that way isn't right. Doers must be imaginers, right? Because you have to imagine the consequences of different possible actions. Right. And so I think this whole picture gives you a wrong architecture for how things go, because it suggests that you need something more than intervention to get to the counterfactuals, but you can't do the intervention part properly without essentially committing yourself to counterfactuals.
Yeah, no, I think that's a fair point. I don't take too seriously the interpretation that as being there are certain kinds of agents that can do one thing but not the other. But I think we can certainly interpret that as there are some kinds of models that can do one, not the other. And that's what I discussed here. And I think Bell is taking perhaps his particular hierarchy of models as somehow standing for agents out there in the world which have those models in their mind. And as you point out, that may not be a sort of clear-cut distinction.
Okay, so maybe I can ask something as well. So I was wondering about kind of the context of this framework you've been presenting. So do you think, because you mentioned Bohmian mechanics and that different interpretations would have kind of different notions. So do you think it's the main application of this will be in kind of the foundational aspects of understanding theories, or do you think it's also a framework that you would see used in applications, for instance, for understanding experiments or so?
I think at a first instance, I imagine that it will be more useful as a pragmatic tool, in the same way that classical causal models are useful as a pragmatic tool. And there's a lot of people in this audience that use classical causal models. If we know that they must be false, right? Because of Bell inequalities. That doesn't mean they're not useful, right? And likewise, I think if we are talking about, say, if we have quantum agents trying to decide about actions involving counterfactual questions or interventions involving quantum systems, something like these models will be pragmatically useful, whether or not they correspond to, they correctly correspond to the ontology of the world. Even if Bohmian mechanics is true, we might still code our quantum AIs with something like these tools to reason about quantum systems in the same way that we may code our classical AIs with classical causal models to reason about the world. But yeah, and as I mentioned, we already know that quantum causal models have a limitation in need to be taken seriously as a foundational model for causation in the world because of the measurement problem, because of things like fitness friends scenarios. But I think an interesting question is whether they can be extended, they can be modified, perhaps in a relational sense. That maintaining some features of the formalism, the main features of the formalism, in the same way that quantum causal models have extended classical causal models. I imagine that it could be something different that would be a further extension. But if it were useful, it would be useful in very remote kind of situations. Perhaps potentially, if one day we have, large quantum computers with running complex AIs in superpositions of different observations, etc. Something like that might be, who knows, might be useful for those kinds of agents or for us in encoding those agents. But that's a speculation. But yeah, then potentially something like an extension of that could correspond to let's say, a correct description of causal structure in the world. But again, that's speculation. I don't know.
Thanks very much. I think time is already quite advanced, so maybe we should thank the speaker again. And if there are more questions, maybe feel free to get in touch directly.
Thank you.